Now, I often take swipes at other subjects telling you why chemistry is the superior subject, and now it's my time to take a swipe at physics. I went through both the IB and the ATAR senior physics textbooks as well as AI, and I could only find experimental observations and they convert those to mathematical equations. So I couldn't find any explanation as to why light might be separated the way it does. So I'll put forth the theory, whether it's good or bad or not, and you've got to have some sort of theory and someone else can then improve on it. So first of all, some general observations. A material will show structural color if there are two things. So one is that the material has a micro or nanostructure small enough to interact with light. So color is also seen with a prism, but this is refraction and it's not under the umbrella term of color refraction. And the second requirement is it must be a repeating pattern, otherwise there will be noise or a lack of intensity to detect by the eye. So you can see with this, an example of lack of intensity is this dull white dolomite mineral or rock, depending on how you're going to look at it and define it. The diatoms have this repeated microstructure. They're called photonic crystals too sometimes, but they are not aligned in a repeating consistent pattern. So as a whole, as a rock, like individually they separate in a microscope and we can see color, but macroscopically we don't see anything. So there's no intensity there. So it's got to be repeated, not just the macroscopic repetition, but it's got to be repeated and aligned and consistent. So looking at the electromagnetic wave, just for a recap, because this is actually for both junior and senior science students, these experimental videos. So hopefully everyone gets something out of that. So we're only dealing with a small part of the electromagnetic spectrum, the visible light spectrum, because that's the only bit we can see with our eyes basically, and it's too expensive to use other instrumentation. And so you can see here the violet has the shorter wavelengths of 400 nanometers, and so that's more waves per second and more energy, and the red is longer, it's about 700 nanometers, and it's got less waves per second, so it's got less energy. So we look at the electromagnetic wave itself as a pulsating electric field with a perpendicular magnetic field moving as a transverse wave through space. Now we're going to ignore the magnetic field because its interaction with matter is less significant than the electric field. So we'll just pretend it's only got an electric field because the electric field interacts with the electrons in the atoms in the matter. And the electric field can then also be moving up and down, or it could be left and right, which is like 90 degrees, or it could be any other angle around a circle. It could be, 45 degrees, not 90, or 360 degrees would be 0 degrees. It's right back at the start. 180 would be the same up and down as well. And also just to recap, because this is relevant from the previous video on calcite mineral polarizing light in two different directions, we saw that the easiest way to polarize light is just to grab some sunglasses that are made out of plastic because they've got very long molecules all lined up. And this causes the light that's in parallel to the molecule to interact highly with the material, and so it's absorbed, and the light coming in at a 90-degree angle to it is not affected by the material and passes through. As a result, the light is mainly just oscillating at one particular angle, which is 90 degrees, or if you add 180, the 270, so down, up, or up, down. And this is evidence that it's just the electric field that interacts with the matter. And so just to go back to prisms again, which is not structural color, again, it's just relevant to what we're talking about. So the theory of forcing light through a material means the wavelengths. Now, I got this from one of the professors that was quoted on the Veritasium video. So this is a theory that is put forth already. I couldn't find one on the slits. I'll just throw one up there for you. So the theory of forcing light through a material means that the wavelengths with the most energetic fields cause the most disturbance to the electric fields in the atoms of the material. And he describes it slightly differently, but I'm just going to say this is resistance caused to the light to slow it down. And so from the previous video from Huygens wave theory, I've got a video on that. You can see that slowing down individual photons causes all those new little wavelets to create a new wavefront that is bent. And the wave shows itself to then bend more. So the red light has less energy and moves with less interference. And so from a previous video also on electronic band theory on what's transparent or not. That sort of makes sense as well, because the photons don't have enough energy, and so they go straight through the material, and so the red light also has less energy and it has less interference, and so it is reflected less in a prism. Okay, so that's kind of relevant, because then we have to have a theory of why it doesn't work with slits. So what's going on with a slit? So I'll throw up the theory. So when light is moving through a slit, you find descriptions and mathematical calculations, but no explanations in the physics material that I could find. Hence, I'll put one out there and you can improve on it. It's like saying, like the Greeks had, there's only 5 elements: earth, air, fire, water, and ether. It's not 100% correct, but it's really important to have a theory that you can work on. So my theory is that the photons are, for the most part, free to go straight through the slit, and that's why you get the intense concentration at like a 0 degree angle. A straight line just hits the back. And then if the wave has a high energy electric field, then it'll be less affected by the electric field that it passes through on the edge. So I looked up the paper. It's about 100,000 nanometers in thickness. So the atoms there will have an electric field, and the electromagnetic light wave will go through it. So will go along the edge of it and touch it. So a low energy red light will be far more likely to be influenced by it. Okay, and so that'll turn, and a purple light less so. So an analogy might be like the gravitational fields of planets that we use to turn satellites around. So that you've got to make sure the speed, it's not too fast or slow, it's not too close to the planet, because the gravitational field will be stronger or weaker. You've got to get all those things just right. Otherwise, the satellite will come out at the wrong angle and will bend at the wrong angle and go in the wrong direction. So that's my explanation of why this is opposite to a prism, and the violet light bends less than the red light. Okay, so that's out there. Someone else can make it better. Okay, and now we know there is some bending around the slit surface. We can appreciate that some waves will add constructive interference, and some waves will be opposite to each other and destructive interference, and stop an intensity line coming, or intensity of light coming through. And so that gives us these diffraction patterns shown here. So here I take, now I'm doing some experiments where I'm taking the slits. Now they're not small enough, they're not the nice, but they still work. Okay, so there's 160,000 nanometers down to 20,000 nanometers. Be best if it was 600 nanometers, but that's what we have. Okay, so the ideal diffraction interference is when the slit width matches the wavelength. So sorry, it's 500 because it's green light. But the problem with this, they've found, is because you're getting such a small slit, there's a decrease in intensity and you can't see it because it gets so dim. And so that's why they use these ones from like 20,000 nanometers onwards, upwards. So there's enough light for us to see because the intensity is not good enough. Okay, even though the small slit actually does a better job. Okay, so it's a balance between diffracting better and seeing it because it's strong enough. Now, from now on, we're now going to go to increasing. So the slits are sort of all the same, and it's assumed so. And we're just going to increase the number of slits. So we're going on the second point of structural color, which is consistency and repetition now. And so now we have 2 slits instead of 1, and the slits are decreasing in distance from each other. So the width is just assumed constant, and you can see that we go from like the distance between 2 slits is 325,000 nanometers down to only like 50,000 nanometers, and you can see the distance between the gaps is much better. The diffraction's much better when the slit distance gets closer and closer to the ideal numbers, which is a lot less than 50,000 nanometers, by the way. So let's just go crazy and do multiple slits. So we're going much better repetition now. So this multiple slit, again, the width is an unknown, and so there's only a sort of maybe 1,000 nanometer gap between the slits because there's like 600 slits here, and so I'm actually doing this video for my Year 8 rock class because this is how I need to show how rocks have colors. And the rocks are way, way better as they don't have these restrictions and they have much better geometry. They have much better repetition, much smaller sizes, and so they have much more spectacular results, to be honest, except for the CD, which I'm going to show you at the end. And the green light here is easily the brightest and most distinct separation compared to the double and single slit. And then if you would just grab the whole lot now, we'll just grab white light. You can see it gives the nice full rainbow with the reverse spread, which is reverse from what the prism is, which we talked about earlier, why that is so, okay? Now let's go on to the CD. There's two other repetitive nanostructures I need to talk about for the sake of rocks. One of them is, the next structure will be the repeating surface markings. So you can see by angled grooves called blaze gratings, or the smoother pattern. Now, my issue with physics, besides it's not trying to understand and give you theories as to why things are going on, and it's just describing things mathematically, which kind of makes me feel like it's as bad as biology, just describing stuff. And these diagrams, they demonstrate. By the way, the one on the bottom demonstrates that it doesn't have to be reflection; it can actually be refraction and go through and do the same repetitive bending. Whereas we're working with the top diagram, which is reflection, which is some repetitive bending. So to make sense, you need to take into account the perception at the point that it enters the eye, and it helps to make it to scale also. And that's my issue with these physics diagrams. They don't actually make sense and describe it. So the first one I've shown you here is I've covered ray diagrams in the previous video, so so you can have a look at that. So I'm assuming you know how to do ray diagrams, and this is just another example of why they're so essential to understanding. So normally all the light here is entering the eye from the full range of visible light from a full range of angles, and there's no constructive or destructive interference. So I looked up the numbers to draw a ray diagram to scale. So the first one's 300. And what you can see is the light rays that come into your eye, they're all differing by about 300 nanometers. And the other light rays miss the eye, or they're redirected from other angles due to the shaping of the surface. So in effect, the eye is receiving only constructive interference for wavelengths of around 300 nanometers. So the nerves in your cone cells are just stimulated for that. And so the perception is that's what you'll see, just 300. And I don't know if you can actually see it. It's probably UV. It might be some purple. But the next one's 500, so that's the greenish color. And again, you can see only wavelengths that differ by about 500 nanometers will reach the eye. So there will be constructive interference at 500 nanometers again. So the cone cells will think, oh, there's just green light present. And so moving on to the DVD slide here, this is good because you've got easy access to it. Interestingly, it's not perfect repetition because it's not meant to be a diffraction grating. It's just meant to play music. So it's got random binary code of pits going up and down, but it's repetitious enough to give you very nice vivid colors, and more interesting enough that the nanometer sizes are almost perfect. And so again, I've drawn this to scale. You can see at the angles I've drawn with my eye and the light, and so I should expect to see blue light close to me and red light further away. And I lined this up with the light in my eye, literally with the piece of paper there. So the angles, I lined up the angles with the paper physically and the actual disc on the page where it's meant to be. And the colors match perfectly. So the wild thing is that, this technique's so powerful, you can practically look at something and you could possibly know what the macro and microstructure of a material is just by looking at the colors that come out from it. And lastly, I'll talk about rocks later, but I need to just mention this one as well. So thin film interference. Again, the physics diagrams give us little relevance and more mathematical descriptions akin to just memorizing something like anatomy and biology. I did find an old school textbook diagram that demonstrates how it should be drawn. So it convinces me that the new generation of science educators, we're failing to teach science. And we probably did a better job, the old school teachers. So just a summary, any micro or nanostructure that's around 10 to 1,000 nanometers in size, ideally, could be bigger, and is consistently repetitive, from the demonstrations, that also can be larger but less effective, will cause some sort of constructive or destructive interference of the white light. Hence, you'll get some sort of color demonstrated. So in physics, this is just generally termed structural color. And some technical terms for these structures that we covered were like slit gratings, laser gratings, and thin film interference. But my students know I dislike English because learning those terms and applying them potentially, you can potentially not understand anything. So it's hopefully this video has let you understand why I'm taking swipes at biology, physics, and English, because you need to be able to think like a scientist, which is different to using a correct term. Okay.